Hello, and thank you for checking out our paper. My name is Luis Chamon, and in this video, I'm going to go over how constrained learning theory allows us to control the behavior of data-driven solutions. So let's jump right in with the why we would want to do that. Learning has become a core technology in modern information processing systems and is now found everywhere, from industrial to medical to smart applications like smart homes, smart grid, and smart cities. This ubiquity means that today, learning affects real societal impact. However, learning often fails and fails catastrophically. There's a growing number of reports showing machine learning solutions to be prejudiced, biased, and prone to tampering, so curtailing their behavior has become critical if we want to use these solutions in a consistent and safe manner. Now we know basically two ways to impose requirements on learning systems. The first one is based on designing models that embed the desired properties directly into their structures and is quite common to impose geometrical invariances. However, while the solution meets the requirements by design, these structures are challenging to devise, especially when the relation between structures, coefficients, and outputs is poorly understood. So think of nonlinear models such as neural networks. So these solutions are hard to transfer between applications and often impossible to combine. Now, another way to impose requirements is by adding penalties that promote the desired behaviors directly to the optimization objective. Now, this regularization approach is quite attractive due to its simplicity and ability to simultaneously address multiple requirements, but despite its widespread use, it does not guarantee that the solution meets the requirements, especially for non-convex learning problems. Since it would seem that modifying classical learning tools cannot fully address the issue of specifying behavior during learning, we set out to develop a new theory of constrained learning so that we can provide tools to learn under requirements. Now let me start by clarifying that what I mean by constrained learning is exactly what you are thinking about. We just take the classical learning problem of minimizing unexpected loss and add constraints. While this constraint problem is easy to write down, there are two obvious challenges to actually solving it. First, the optimization variable is a function, which makes constrained learning an infinite dimensional problem. Second, we only have access to the data distribution through samples, which means that we cannot evaluate any of the expectations that we wrote down. So throughout the rest of this video, I'll show you how to overcome these obstacles by answering basically three questions. Before anything else, is this problem even worth solving? Would constrained learning allow us to address the issues we raised in the beginning of this video? Then, we should say what exactly we mean by solving here. In view of all the challenges we have, what can we actually expect from a solution? And finally, having dealt with all these preliminaries, we can get to the main course, which is constrained learning tractable, and if so, how? So let's start by answering the first question by giving a concrete application example. Now suppose that we are trying to predict whether an individual makes more than $50,000 a year based on their personal and socioeconomic data. Using classical learning, the resulting classifier turns out to treat men much more favorably than women. All things being equal, it is almost a full percentage point less likely to predict high income for a woman than it would for a man. In fact, in more than 3% of the cases, the classifier would switch its prediction from high to low income if the individual had been a woman. And removing gender from the predictors only makes things worse. So if we want to train a classifier that is agnostic to gender, we have to constrain that its output be similar whether the individual be a man or a woman. Obviously, fairness is not the only type of statistical invariance that we can impose using constrained learning. We can also formulate robust learning problems, do explicit transfer learning, deal with unbalanced datasets. And there are also many learning tasks that can be posed as constrained optimization problems like semi-supervised learning or training autoencoders and generative adversarial networks. So developing a theory of constrained learning would also help to ground some of the reformulations and approaches that people use to tackle these problems in practice. So it would seem that yes, constrained learning problems could be used to impose requirements on data-driven solutions. We just don't know how to solve these problems. And that brings us to our next question: what does a constrained learning solution look like? Since the problem we want to solve is infinite dimensional with unknown statistics, we can't really hope to get a definitive solution. So instead, similar to classical learning theory, we seek a probably approximately optimal one. By that I mean that we will settle on a margin of error, epsilon, and a probability of failure, delta, and we will look for a solution phi dagger that is probably near optimal, which means that it's a solution whose value is close to the optimal one with high probability. Now, if this looks familiar, it's because it's directly related to the idea of probably approximately correct or pack learning. But this is not enough for us because we also have to take into account the constraints. So we require phi dagger to also be probably approximately feasible, by which we mean that the solution is almost feasible, again with high probability. So from now on, when I talk about solving constrained learning problems, you should keep in mind that I actually mean finding a PA-opt solution. Now, having settled that, let's move on to our final question. Is it possible to get the PA-opt solution for constrained learning? To answer that, let's first get some inspiration by looking at how classical learning does it in the unconstrained case. So the idea is to first get rid of the infinite dimensionality by parameterizing phi using a model f. Now, the optimization is over a finite dimensional parameter vector, theta, and for that we pay a price that depends on how good the model is. It's worth noting that common parameterizations like neural networks or kernel models often enjoy much stronger universality properties than the one we wrote here. So let's move on to the expectations that we can approximate by averages over the data samples, and then we get the widely used empirical risk minimization problem. Now, the fundamental theorem of learning guarantees under some mild assumptions that the solution of this finite dimensional empirical problem is close to that of the infinite dimensional statistical one. Okay, so we might be tempted to try the same thing for constrained learning, but unfortunately, it doesn't work. The issue is that the optimization problem resulting from parameterizing phi is typically non-convex, and while this wasn't really an issue in the unconstrained case, it became one as soon as we added constraints. Not only have we lost all approximation guarantees, but it's not even clear how we should go about solving this problem, especially since we can't rely on its dual because we can't guarantee strong duality anymore. Fortunately, it turns out that we don't really need to worry about that because we can directly relate the empirical dual to the original problem. And that's the main result of this work. Probably approximately optimal constrained learning can be done by solving an unconstrained, finite dimensional empirical problem. In other words, we can replace the problem we want to solve by a problem we can solve. Now, this is worth repeating because it's the main point of this paper. Constrained, infinite dimensional statistical problems can be solved through unconstrained, finite dimensional empirical ones. Now, if we look at what's going on inside these error terms, we see that they depend basically on three elements: the quality of the parameterization, the difficulty of the requirements, and the number of samples. In even finer detail, we can improve the near optimality gap by using a richer model class, like neural networks or kernel models, but the impact of these improvements is going to depend on the difficulty of meeting the constraints. That's quantified by lambda star p, which are the optimal dual variables of a related learning problem. Now, we can also close that gap by increasing the number of samples, but this is again mediated by the model complexity through the VC dimension, or DVC. The thing that's interesting to note here is that constraint satisfaction is really only affected by the number of samples. So it turns out that we can solve constrained learning problems by using an unconstrained finite dimensional optimization problem. Now, to illustrate how, let's go back to our fairness application. So using the constrained learning theorem, we can rewrite our problem as an empirical dual and then use a primal dual algorithm to solve it. Now, we know from classical duality theory that the outer maximization problem is convex, and we can just use some subgradient ascent to solve it. Now, the inner minimization, though, may not be convex, but if we can find an approximate minimizer, that's often good enough for the algorithm to work. To illustrate this fact, let's use a neural network trained with stochastic gradient descent as a parameterization. Of course, you don't need a neural network for this problem. I mean, logistic regression would do the trick. It's simply that we can see how the primal dual behaves in a non-convex setting for which there's ample evidence that gradient descent reaches good local minimizers. So after this algorithm converges, the result is a classifier that has almost the same test accuracy as the unconstrained one, but is considerably less sensitive to gender. Before concluding, let me go over a few side notes. So to deal with the constraints, this paper assumes that the loss functions are convex, even though the final learning problem is not. It turns out that this assumption can be lifted by imposing some mild conditions on the data distribution. Another thing that I sort of brushed over was the use of primal dual algorithms to solve the empirical dual problem. Now we know that in general these algorithms need not converge for non-convex programs, but some guarantees can be given in specific cases. These are both topics of works to come. I also wanted to point out that constrained learning theory also applies to other settings, like to impose safety requirements on policies obtained using reinforcement learning. So let's now conclude by going back to the questions we have answered throughout this video. So if you fell asleep and just woke up, no need to rewind, this slide is the whole message. So we showed that constrained learning does enable learning under requirements and can be used, for example, to train fair classifiers. We also saw that despite the challenges posed by the constraints, we can probably approximately solve constrained learning problems using their empirical duals, and then showed that the quality of this approximation depends in a nice way on the number of samples, the model complexity, and how stringent the requirements are. Now, unfortunately, I can't really answer any of your questions right now, but you can find more information on this work and other ongoing research on my website. And if you still have questions or feedback, please feel free to shoot me an email. Thank you very much for watching, and before you go, don't forget to like this video by clicking on the what now? I know it's not YouTube, but you don't think they're gonna have a like button? I mean, still, I can say just in case. I mean, I don't think anybody's gonna